Hello, everyone. I'm Gilad Shainer, and I manage the InfiniBand networking at NVIDIA. I'm going to discuss with you the new generation of supercomputing architecture called cloud-native supercomputing, and how the ARM-based DPU, data processing unit, enable us to actually design and bring this technology to market. So first, looking a little bit backward, multiple years ago, scientific computing mainly consisted of first principle simulations and basic visualizations done in a centralized data center. Today, scientists are fusing traditional simulations with deep learning, big data analytics, and streaming edge computing to solve the mysteries of the world. These demanding workloads rely heavily on a smart, fast, reliable, secure networking, all the way from the edge into the large supercomputer storage and the various appliances. InfiniBand is the leading high-speed networking for high-performance computing, for deep learning, for the large cloud infrastructures. The InfiniBand network consists of the network adapter, the ConnectX, the Bluefield data processing unit, or the DPU, which will be the main focus on my presentation today, and the quantum switch, NVIDIA quantum switch. Those components enable a high-speed, low-latency, RDMA-based data movements from storage to compute or between compute within a data center and going all the way to the edge. Beyond of those components, there are several appliances that bring extra capabilities into InfiniBand data centers. The MetroX appliance enabled to extend native InfiniBand, native RDMA, reach over long distances to connect between remote InfiniBand data centers and create a virtually larger one, to connect between an InfiniBand data center and a remote storage for disaster recovery, and even connect the main data center to a workstation sitting in a scientist desk, under a scientist desk, to be able to move model quickly from the workstation into the main system, or as well for fast visualization. The Skyway Gateway seamlessly bridge between InfiniBand on one side and Ethernet on the other side, enabled to connect remote Ethernet connectivity into an InfiniBand data center, InfiniBand supercomputer, and vice versa. And UFM Cyber AI appliance, it's an appliance that enables enables network management, orchestration, connects to job schedulers, for examples, and so forth. The UFM Cyber AI appliance also reads telemetry information from the network and build an historical database of telemetry information. And on that database, it runs deep learning algorithms to look for anomalies, to enable predictive maintenance, to bring more security into supercomputing. So in my talk, we'll focus on the DPU and how the DPU enables the cloud-native supercomputing architecture. So first, what is the DPU? The DPU, or data processing unit, it's a full data center on a chip. It includes all of the ConnectX adapter interface, or IP, all of the network functions, multiple ARM cores to bring compute that sits next to the ConnectX, multiple acceleration engines that can increase infrastructure management workload performance and capabilities, as well as to accelerate other kind of algorithms, other sort of high performance algorithms. There is a memory interface with memory on a card and PCI Express switch that enables to connect a DPU to PCI Express devices. It could be GPUs or flash devices and so forth. So the DPU, it's a full data center on a chip. It's the basic component of a data center. Now, what are we using the DPU for? We're using the DPU for 3 applications. One application is edge computing. As we all know, there is a great increasing bottleneck of capabilities to analyze data because we needed to move data from where we source data all the way to the main system, just doing the first analysis. In order to overcome these bottlenecks, we actually want to move compute to where the data is. We want to build computing elements where we source data. We want to bring edge computing capabilities to the labs. And the DPU is the basic component of a data center. So we can bring the DPU into the lab and have the DPU become the basic edge computing device. The DPU can do the first analysis on the data where we source it, and then send it RDMA way into the main supercomputer. If one DPU is not enough, obviously we can pack multiple DPUs together, or have DPUs and GPUs together to form different sizes from compute capacity of edge computing. The other 2 applications of the DPU are primarily within the data center. One of the most challenging applications in data center today, it's the data center operating system. It's the infrastructure management. It's dealing with security, dealing with the increasing number of tenants, dealing with the storage management and so forth. This is an application that takes a heavy toll on the data center CPUs. And that's why when we're looking on multi-tenant systems today, when we look on cloud infrastructures, we see that those clouds cannot really deliver bare metal performance because their CPUs needs to run the data center operating system as well. They need to run the infrastructure management. They need to bring security between the tenants to support multi-tenancy. And even more than that, running the security as part of the data center operating system on a CPU means that we're running the security on an untrusted domain because the CPU is the same domain that actually runs the applications. So it's not the ideal domain to run the data center operating system. Now the DPU can actually solve that problem. First, the DPU sits in a trusted domain. It's not a domain that hosts the users. The second, the DPU is actually built to run the infrastructure management. It is built to run the data center operating system. It has specific engines for security. It has specific engines for file system, for storage. And therefore, with bringing the DPU into the data center, bringing the DPU to every server, enable us to move or migrate the data center operating system, the infrastructure management, from being managed and executed on the CPU to be managed and executed on the DPU. That frees CPU cycles. That frees a lot of CPUs. So with the DPU, we can now, for the first time, combine bare metal performance and multi-tenancy, combine bare metal performance and security. And that's the essence of cloud native supercomputing. Combination of bare metal performance and multi-tenancy and security support. Now, even more than that, having the DPU in the system enable us with a Linux machine that sits in front of a Linux machine, a computer that sits in front of the computer, a computer that can do pre-processing of data before it goes into the CPU or the GPU, which means we have a new accelerator. And the cloud native supercomputing bring us bare metal performance and multi-tenancy isolation, but also create a new level of accelerations with a hybrid model of a GPU, CPU, and a DPU. So let's look into more details. First, how's the software architecture looks like? So in a traditional supercomputer, all the management, isolations, and monitoring is running on the host. That's why you don't see much of a security in supercomputing, because when you do it, you lose the performance capabilities. And as we know, supercomputers are all about performance. The file system, cluster file system, network file system is also running on the host, which is another toll on the CPU. So we are taking those workloads, we're taking the data center operating system, moving that from the host, from the CPU, into the DPU, into Bluefield, and leveraging the SDK, the software development kits, Docker and Magnum IO, to bring the services, to enable the services that supports all of the infrastructure management. We're also moving more elements of HPC-AI communication frameworks, such as MPI, or MPGAS, or Nickel, and moving those into the DPU as well as part of accelerator, as part of accelerating those workloads, as part of bringing the ability of overlapping between compute and communication. So when you're running communication, such as the communication frameworks on a CPU, you are mostly in the cases where the CPU needs to run compute, communications. And if we move the communications into the DPU, we can run things in parallel, achieve 100% overlapping. So it's not just bare metal performance, it's actually accelerated bare metal performance with multi-tenant isolation. So on the security part of things, as we all know, we want to bring more users to the supercomputers that we build. We don't want to have to trust the end users. We want to isolate between the end users. We want to secure between the end users. We want to provide job isolation and performance isolation. And this is what the DPU enables us to do with moving or migrating the infrastructure management to run on the DPU. It enables us to move toward a zero trust architecture in supercomputing, to provide SLAs. On an InfiniBand supercomputer, we can support more than 32,000 concurrent isolated users on a single subnet, supporting more users in a more secured way. From an acceleration perspective, the DPU can do data arithmetics on the data before it goes into the server, before it goes to the CPU or the GPU. So we can move collective operations. We can move non-blocking collective operations from being run on the CPU to actually run on the network, on the DPU. We can deal with active messages, with smart MPI progression. We can do compressions and decompressions on the DPU. We can actually use the DPU to run any sort of approved user algorithm, moving us to a new level of hybrid compute infrastructure. And how we offload work into the DPU, we have created processes that runs on the DPU. They're called DPU workers. Those workers can get metadata from the host processes and then perform local RDMA operations or remote RDMA operations to actually go in and move data between memories of different hosts and do arithmetics with no interference of the host CPU, with no overhead of the host CPU. So if we take two examples of taking non-blocking MP operations such as all-to-all and all-gather, we can see that we can dramatically improve the performance of these non-blocking operations by pipelining them into the DPU. And not just that, as we move the non-blocking MP operations into the DPU, we can achieve 100% overlapping. So moving from almost 0% overlapping, because everything runs on the CPU, to 100% overlapping, where the CPU runs the compute, DPU runs the network or the communication. And that enables us to actually improve application performance. So we took the three-dimensional FFT as an example. Three-dimensional FFT runs on all-to-all operations, MPI all-to-all operations. We modified that to run on a non-blocking all-to-all operations, and we're able to achieve great performance boost with the DPU. So now we get bare metal performance, but actually accelerated bare metal performance and the security part or the multi-tenancy support. We have created Docker, which is the software development kit for the DPUs. Docker exposes all of the services to the applications, all of the DPU services to the applications, the networking, the storage, the security, the telemetry, the MPI services for acceleration perspective, exposing those services to the applications running on top. And then those applications, or these applications, infrastructure applications or MPI applications and so forth, can leverage the DPU to move the work to be done on the DPU. We have released the first generation of Docker. There will be more capabilities being added to Docker over time to expose more services. And a great part of Docker is that everything that is written to run on Bluefield 2, the current 200 gigabit per second data processing unit, will run as is, probably faster, on Bluefield 3, which is the 400 gigabit per second generation DPU that will release in the future, as well as Bluefield 4, Bluefield 5, and so forth. So the DPU bring us great capabilities. First, for edge computing. Second, inside of the data center, it helps us to move or migrate our supercomputing architecture to be cloud-native supercomputing. For the first time, to be able to combine bare metal performance, accelerated bare metal performance, with secured and multi-tenancy support. I encourage you to check NVIDIA website on the section of cloud native supercomputing. You can find there multiple white papers and more information on how to get the SDKs and the rest of the components. Thank you very much for listening.